Welcome. Today we look at partial derivatives and partial differential equations. So we are dealing with functions of several variables. We can therefore also differentiate with respect to several variables. Let's take the function fxy is equal to x cubed y squared. It's a nice function of two variables, and if you differentiate with respect to x and keep y constant, we write it like that. We say partial x fxy is equal to 3x squared y squared. So we keep y a constant and we differentiate with respect to x. Now, because this is so cumbersome to write, there's an abbreviation which is just fxxy. So that's called the partial derivative with respect to x. And in the same way, we can define the partial derivative with respect to y. And this is then 2x cubed y. And we write also fy xy. So these are called partial derivatives. Now we can differentiate more. We can differentiate twice. So if I take the second derivative, fxy, so we take this function and we differentiate it again with respect to x, we get 6xy squared, or we can also differentiate twice with respect to y, fxy. So we take here and we differentiate with respect to y, and we get 2x cubed. We can also differentiate with respect to x and y. So first differentiate with respect to here with respect to x, and then with respect to y, fxy. So we have that. We have already computed the derivative with respect to x. Now we can differentiate with respect to y, and we get 6x squared y. But we can also go the other way around. We can take the derivative with respect to y first, and then the derivative with respect to x. So that's here, so that gives 6x squared y. Now also here we use abbreviations. We call this fxx, we call this fyy, we call this f first x and then y, and this is fyx. So these are second derivatives, and these are mixed derivatives. Now you might wonder, why is this an accident that these two things are the same? No, this is not an accident, and the next section is Clairaut's theorem. Clairaut's theorem will tell us that they are the same. So Clairaut's theorem tells us that this mixed derivative fxy and fyx are the same. So we have to assume that f is twice differentiable. Meaning that if you take the derivatives, these mixed derivatives, they are continuous functions, so continuously differentiable, then fxy. So this is already an example of a partial differential equation. It's an equation for a function f, and these are partial derivatives. We will come to this next. So this is a beautiful, beautiful theorem, and let me just prove you that quickly. So we look at quantum derivatives. So the difference quotient has a fancy word, and it's quantum derivative. So we have fx plus h. So if you look at fx, xy, this is about the same thing. Then 1 over, let me just take that, 1 over h, fx plus h, y minus fxy. So what I do here, I will take the 1 over h. This is h is a small number. I will take this small number h on the other side. Now if we take the if we take the second derivative, we get fxy. That gives us another h here. So this is about, and then we take this, what we have here, fx plus h, and then y plus h, minus fxy plus h, and we subtract fx plus h, y minus fx, y. So that's a discrete expression for the second derivative. By the way, if you are working with computer vision, this is what you do. You take differences between pixels, adjacent pixels, and so you can also define the second derivative in computer vision, which is very important there. And then we can also do the hfy xy, which is about fxy plus h minus fxy, and then we take h square fyx. Now we take the derivative with respect to y, that is with respect to x now, so that's x plus h, y plus h, minus fx plus h, y. So we have just evaluated that at x plus h, and then we take that whole thing away. fxy plus h minus fxy. Now, let's see. Candy Crush time. What we have, fx plus h, y plus h. We have to compare these two things, right? This and this. So they're actually equal. You can see they are equal because they are. We can see this part here. We can see this part. Fx plus hy, that appears here, but it also appears here, also with a negative sign. Then we have fxy plus h, that's here. Fxy plus h is here. And finally we have the last thing is fxy. That's it. So this is really the same. So these quantum second derivatives are the same. Now take the limit. That's what we do in calculus. We take the limit when h goes to 0, and these become the usual derivatives. And we take the h squared on the other side, and we see if the limits exist. If these limits exist here, that's where we use the second derivative. If the second derivative is nice, then we have seen that fxy. So here's an example showing that if we have not enough smoothness, that the Clairaut's theorem fails. So what we take is fxy is equal to 4xy y squared minus x squared over x squared plus y squared. So let's just look at this this function. This is actually a continuous function, and if you look at it in polar coordinates, remember polar coordinates is with x is equal to r cosine theta, y is equal to r sine theta. So this is actually just 4 r cosine theta, r sine theta, r square cosine square theta, minus r square sine square theta, over everything over r square. So we can cancel the r's here, this r square. We can write this here. This is actually, this is just 2 times sinus 2 theta, and this is an r square, and this is cosine 2 theta. So this is This is 2 times sinus 2 theta cosine 2 theta times r square, which is just sinus 4 theta times r square. So in polar coordinates, this is a very nice function. And what happens here is that the second derivative is actually no more continuous. If you take fx, x0y, you can compute that, it's just 4y. It's a little bit a hike to compute these derivatives, and so that means that fxy xy 0 0 is just equal to. Now you can also take the derivative with respect to y. Fy x0 is just minus 4x. Again, this is kind of, you take this just twice the derivative, and then you plug y equal to 0, and you get minus 4x, and fy x0 is then just minus 4 at 0. So you see, fxy00 is not fyx00. Okay, let's briefly look at partial differential equations. Partial differential equations are equations for an unknown function f, which involve derivatives with respect to several variables. So here, this is an example of a partial differential equation. This is an example of an ordinary differential equation because only derivative with respect to one variable appears. And it's a rich story. This is the fabric of space, the fabric of us, the fabric of the world. Everything is made of partial differential equation. Especially if usually we use t as a time parameter. So and x is space. So t is time. So if you have that f of t of x, then this is time, and this is space. And let's just look at a couple of equations. So I want first to look at the transport equation. So it is the simplest partial differential equation you can write down. So we have ft is equal to fx. Now there is an interpretation to this, a dynamical interpretation. So let's look at this function. So this is x. This is f of, we write here f of t of x. But at t equal to 0, we can write down a usual function, right? We have at x equal to 0, maybe this function looks like that. So that's at t equal to 0. Now let's look what this equation tells us. This equation tells us that the time derivative is equal to the slope. Fx is the slope. What's the slope here? When the function goes down. So the slope is negative, which means that the function will decrease here, while here the function will increase. So wherever the slope is positive, it will go up. And what happens is, you can kind of see when you push down here and you pull up here, what happens is that this function will after some time look like that. Maybe that's at t equal to 1. So what happens is this signal has moved over. And that's why it's called the transport equation. Actually, if this function here you call g of x here, so if you call this g of x, which is f of 0 of x, then the function, we can write down the function explicitly. We can write down ftx. It's just gp plus x. And you can double check that if you take this this function differentiated with respect to t and with respect to x, you get the same. The next thing is the heat equation. For the heat equation, we have a second derivative with respect to x here. So that's also interesting. That's probably the most important partial differential equation overall. So that's x. And let's just assume we have here an initial function like before. We have an initial function, something like that. Maybe I'll make it like that. So this is the function f at time t equal to 0. Maybe this is at time t equal to 0. Now, what happens is we have the second derivative here. So what happens at this point here? Say here. What is the second derivative of fxx here? You should see the second derivative is negative. So it's negative, this whole thing goes down. Here the second derivative is positive because it's concave up. So the function goes up. Wherever you have a bump, here the bumps are pulled down and the sinks here, they are pulled up. So what happens is after some time, this function has just smoothed out, maybe at t equal to 1. And that's what happens with heat, it diffuses. It's also called diffusion equation. Now it's not only important in physics, also in finance. For example, this Black-Scholes equation, which is an infamous equation in finance, is a partial differential equation which has been used a lot in finance. This you can reduce to the heat equation. Wave equation is everywhere. Sound, light, everything is made of waves. Quantum mechanics also is a wave theory, the Schrödinger equation here. It looks like the heat equation a little bit, the Schrödinger equation. There's an I here. That I makes it actually behave like a wave equation. So what we have here is a kind of a, maybe the most common picture is you have a kind of a string. You have a string which you shake. I will show you a movie in a second. And what happens, just explaining what this law tells us, it's again fxx which matters. Fxx is negative here. So what happens is that, but that's an acceleration here. Which is also a force. So there's a force pulling this down and a force pulling this up, force pulling down. And so at a later time, what happens with this string, it will just maybe look like that. Okay, finally we look at Berger's equation. This is the most fun. This is when you are at the beach, right? So this is the water here. And there's a wave coming. There's a wave, and you are at the beach here, nice sand, and so you're sitting here in a chair, and there's also kind of a nice umbrella. So you're sitting at the beach and this wave here is approaching, and actually this wave satisfies this partial differential equation. So let's see, this can be understood by looking at if you look at the transport equation with a constant c here, this is solved by f of t of x is equal to g ct plus x. So you can double check that this is the speed here. This is speed. You translate with, this is a transport equation where you move with speed c. You can check if you take the derivative with respect to c, with respect to t, you get c times the derivative with respect to x. Now what happens here is the speed depends on the height of the wave. So the speed depends on the y. Speed depends on height. Actually the speed is the height, and what happens then, this goes faster over than here. So this wave moves faster, and so what happens at the later time, right, when you look at this wave at the later time, so maybe this is at t equal to 0, at the later time what happens is this wave will fall over, and that's what you observe when you are at the beach.